Okay. Uh, Today we are discussing only the objective questions that they are asked in at October 21. Okay. So we are going to the first question. Okay. A graph can be used to represent the motion of an object. Okay. Here they show a quantity versus time graph. Okay. Which row in the table gives the quantity plotted on the y-axis and corresponding to quantity represented by the gradient of graph. Okay, so here we have to consider different graphs. That means displacement time graph, velocity time graph, acceleration time graph, and what about their gradient? Okay, first of all, the gradient of displacement time graph gives the velocity. Okay, and the gradient of velocity time graph gives the acceleration. Okay, similarly, if we are considering the area under the curve in an acceleration time diagram, we will get the velocity, okay, corresponding average velocity of the motion. Okay. Similarly, the area under the curve in a velocity time diagram will give the distance traveled by a body. Okay. So from these points, we can conclude that if you are observing the options, we will get the velocity, the gradient of velocity time graph will give the acceleration. Okay, so the answer of this question is choice B. For the choice A, the displacement time, the gradient of displacement time graph gives only velocity, so the option A is wrong. Okay, then for the choice C, the gradient of acceleration time graph, we will get jerk, Jerk, jerk. We will get. Okay, again the option D, it is also wrong. Okay, so from this graph, the gradient of different graphs we have to remember. Okay, so the gradient of displacement time graph, it is average velocity, sorry, instantaneous velocity, and the gradient of velocity time graph is acceleration, and the area under the curve in acceleration time diagram is velocity, and the area under the curve in velocity time diagram is distance traveled. Okay, so we have to move to the second question. A massive star exerts a gravitational force F star on a small distant planet. The planet exerts a gravitational force F planet on the star. Which row of the table is correct? Okay, this times they are asking related to the gravitational force. Okay, we know that according to the Newton's gravitational law, the gravitational force is equal to G into m1 m2 divided by r square, where G is the universal gravitational constant and m1 and m2 are the mass of the object respectively. And what about the r? R is nothing but the distance between the two masses. Okay. So from this expression, it is clear that the gravitational force is proportional to the product of the mass, and it is inversely proportional to the square of distance between two masses. Okay. So if you are considering the star and a planet, okay, right? Then and the distance between the star, the center distance between the star and planet can be taken as r. Okay, then the gravitational force exerted by the star on planet is F star is nothing but it is G into m1 m2 divided by r square. Okay, similarly the gravitational force exerted by the planet on the star is F planet is equal to G into m1 m2 divided by r square. Okay, from this it is clear that the gravitational forces exerted by the masses, different masses, are equal in magnitude but opposite in direction. Okay, that means the net effect resultant force is zero. Okay, right? So the gravitational forces are equal in magnitude and opposite in direction. Okay, so from the choice, it is the answer of this question is choice C. That is the magnitude of forces F planet and F star are equal, and their direction of actions are opposite to each other. Okay, then question number 3. Two different springs S1 and S2 are suspended from a fixed support. Masses are attached to the bottom of S1 and S2 are shown, right? The extension of S1 is x and the extension of S2 is x by 3. The elastic strain energy in S1 is E. Which of the following is the elastic strain energy in spring S2? Okay. Then first of all, we know how we can calculate the elastic strain energy. Okay, the elastic strain energy is nothing but half into force into displacement, because the here the force applied is a gradual application of force. So the strain energy is equal to half into force into displacement. Okay, then for the first spring, that means S1. The force applied is nothing but the weight of the mass applied. Okay, it is nothing but is the weight of the mass applied. So the force is equal to, yeah, the strain energy stored in the first string is equal to SE1 is equal to half into F1 into X. Okay, where F1 is the force applied on the first spring and X is the displacement of the spring corresponding to that applied force. Okay, so we can substitute for F1. We can substitute for F1 that we can substitute instead of F1 we can substitute what it is mg. Okay, that is m mass is applied, on the spring S1. So the corresponding force is the weight of the mass. Okay, weight of the mass. So so we will get half into mg into x. Okay, that is a strain energy stored in the first spring. Okay, it is already given that in question, question itself, that given that the elastic energy stored in the first spring, it is equal to E. Okay, capital E. That means half into mg into x is equal to E. Half into mg into x is equal to E. Okay, so then we can find out the elastic energy stored in the second spring, that is half into F2 into x by 3. Okay, why it is that? Here the force applied is F2 and the displacement corresponding to the F2 is x by 3. Okay, now we can substitute instead of F2 what here the force is applied by, the force is nothing but the weight of 2m. Okay, that is the 2m mass of mass is attached to the spring. Okay, this 2m mass is elongated the spring. Okay, so what, so the strain energy stored in the second spring, it is nothing but half into 2 into 2 mg into x by 3. Okay, so just we are rearranging these terms. So that is 2, the rearranging we will get half into mgx into 2 by 3. Okay, just rearranging the terms. Okay, that means half mgx is nothing but it is the strain energy stored in the first spring. Okay, instead of that we can substitute instead of half into mgx we can substitute the value E. Okay, the value E. So we will get the elastic strain energy stored in the second spring is equal to E into 2 by 3. Okay, so what about the answer of this question? Okay, the answer of this question is nothing but it is choice C, 2 by 3 E. Okay, if the elastic energy stored in the first spring is E, then the elastic energy stored in the second spring is nothing but it is 2 by 3 E. Okay, next question 4. A tennis ball is moving through the air. The diagram shows the horizontal and vertical components of its velocity. Okay, which of the following expression gives the magnitude of velocity in meter per second? Okay, it is nothing but it is a right angled triangle, right? Whose and the one of the angle is given, that is 22.6 degree, right? So from the properties of right angle to triangle, we know that sine theta. Okay, if we are taking this angle as theta, okay, if we are taking it angle as theta, then the sine theta is nothing but it is opposite side divided by hypotenuse. Okay, what about it is the base? Okay, the 13.2 meter per second represents the base, and it is the height. Okay, it is the height of the triangle, and this angle is the 90 degree. Okay, so we will get the sine theta is equal to opposite side divided by hypotenuse, and we know that the cos theta is equal to adjacent sine divided by hypotenuse. Okay, if we are applying this equations to this triangle, we will get sine 22.6 is equal to opposite side, or the opposite side of theta is nothing but it is 5.5 meter per second divided by the velocity, that is nothing but the resultant velocity, which represent the hypotenuse of this triangle. All right. So sine 22.6 is equal to 5.5 meter per second divided by the velocity. So we can easily calculate the velocity. The resultant velocity is equal to 5.5 meter per second divided by sine 22.6 degree. Okay. Otherwise, we can also apply the cos theta also to this triangle. Whatever the cos 22.6, it is nothing but the adjacent side. Whatever the adjacent side of this theta, or this angle is 13.2 meter per second divided by the resultant velocity. Okay, so we can calculate the velocity is equal to 13.2 meter per second divided by cos 22.6 degree. Okay, from this calculation we can choose the right choice from the options. Okay, so the choice is C, that is 5.5 meter per second divided by sine 22.6. Okay, so the value 5.5 divided by sine 22.6 and 13.2 divided by cos 22.6, both are same. Okay, both are same values. Okay, then question 5. A beam is supported by a pivot as shown in diagram. The center of gravity of the beam is at G. The beam is acted by a force F, which diagram shows an arrangement where the beam could be in equilibrium. Okay. What about the center of gravity? The center of gravity of a beam is nothing but it is a point at which the total weight of the beam is being to be acted. Okay, that's or the total weight is concentrated point. Okay, so if you are that means at G, what happens at G, the whole weight of the beam is acting. Okay, if you are considering the pivot as a point, okay, point of moment, okay, rotation moment, then what happens, since the total weight is concentrated at a distance from the pivoted point, the beam has a tendency to rotate. The beam has a tendency to rotate about the pivoted point. Okay, just like our door. Okay, just like our door. So what about the direction of rotation of this direction of rotation of the beam due to the weight? Okay, this is the rotation direction of rotation of beam due to the weight. Okay, this is in counterclockwise direction. Okay, it is in counterclockwise direction. Okay, then the moment due to the applied force F about the pivoted point is nothing but it is in this direction. That is just opposite. It is in clockwise direction. Okay, so the moment due to the weight and the moment due to the applied force are opposite in direction. So it could be in equilibrium. Okay, it could be in equilibrium. These are if these two moments are equal in magnitude, then obviously their directions are opposite. So if their magnitude are equal, then the beam could be in equilibrium. Okay, then what about the second condition? In second case, the weight is acting at the center of gravity, and the moment due to the weight is acting in counterclockwise direction with respect to our pivoted point. Okay, right, our pivoted point. And what about the moment due to the applied force F? The direction of moment due to the applied force is, again, if we are based upon the pivoted point, the direction of moment due to the applied force is also in counterclockwise direction. Okay, the direction of both moments are in same direction, so it could not be in equilibrium. That means there is a tendency of rotation of beam exists, because they are in same direction. There is no balancing moment exists in the second case. Okay, just because of the moment due to the weight about the pivotal point and the moment due to the applied force F about the pivotal point, both are in same direction. So there will be a net couple or net moment in the system, so the beam could not be in equilibrium. Then what about the third case? In third case, the weight is acting vertically downward in the center of gravity, and here the moment due to the weight about the pivotal point, it is acted in counterclockwise direction, and the moment due to applied force about the pivotal point is just clockwise direction, and since the direction of moments are opposite, if their magnitude are equal, then the system could be in equilibrium. Okay. Then what about the fourth case? The weight is acting at centroid. It is a weight. Okay. Then what about the moment due to this weight? The moment due to this weight about the pivotal point, it is again acting in counterclockwise direction, and what about the moment due to applied force F about the pivotal point? It is nothing but it is in clockwise direction. Clockwise direction. Okay. So the moment due to the weight and moment due to the applied force are in opposite direction. If their magnitudes are same, then the beam could be in equilibrium. Okay. So what about the correct choice of this question? Correct choice B, in second option, the direction of moment due to weight and the moment due to applied force are same direction, so the beam could not be in equilibrium. It should be rotate about the pivotal point. Okay. Next question. A block of wood is stationary on a frictionless ramp as shown. The block is held in place by a string. The weight of the block is W. The force applied to the block by the string is F. Okay. A triangle of force can be used to determine the magnitude and direction of the normal contact force N acting on the block. Which of the following triangles is correct? Okay. Actually, we have to draw the free body diagram of this given conditions. Okay. Since it's a frictionless dam, there is no frictional forces acting. Okay. So the weight of this block is always acting vertically downward. Okay. Weight is always acting vertically downward. Okay. Then what about the force? That is the string force. The string force is always parallel to the plane. Okay, parallel to the inclined plane. Okay, parallel to the inclined plane. Okay, so we can draw this force. Okay, then what about the normal reaction? The normal reaction means it is a force exerted by the inclined plane on the body. Okay, which should be always perpendicular to the plane. Okay, which should be always perpendicular to the plane. Okay, so we know the three forces and their directions. Okay, weight is vertically downward. Okay, in all the choices the direction of weight is correct, that is vertically downward. Okay, right. Then next case, this force, that is up the force from the string. Okay, that the tension on the string is F, which is always parallel to the plane. Okay, in all the options, again the direction of F is also parallel to the plane. It is right. Then what about the next condition? The normal reaction should be always perpendicular to the inclined plane. Okay, that means the force F and the normal reaction mutually perpendicular. Okay, mutually perpendicular, and it is in this direction. Okay. It is perpendicular and in this direction. Okay, so we will get a exact diagram. Okay, which diagram? The diagram A shows the correct uh, triangle. Okay, which correct triangle of the force representation. Okay, that is weight of the body is acting vertically downward. It is absolutely right. Then the applied force from the string is parallel to the plane. Okay, it is again right. And the normal reaction, it is perpendicular to the plane. Okay, perpendicular to the plane and towards the body. Okay, it is acted upon the body. On the body, it is a free body diagram of our body block. Okay, so diagram A. In case of diagram B, it is just the normal reaction is just opposite direction. Okay, it is not right. Okay, in and the option C and D, the force F and normal reaction are not perpendicular to each other. Okay, in this condition we know that the string force is parallel to the plane, so the string force and our normal reaction should be perpendicular. Okay, should be perpendicular. Okay, so the right answer is A, choice A. Then question 7: a ball bearing force vertically from rest through a distance of 50 centimeter in a time of 0.32 seconds. Okay, which expression gives the acceleration of the ball bearing in meter per second square? Okay, then what are the given data? Okay, this is one of the example of uniform accelerated motion, right? Then for a uniform accelerated motion, we know some equations, that is v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2as. Okay, where v is the final velocity of the motion, u is the initial velocity of the motion in meter per second, and s is the displacement in meter, and a is the acceleration in meter per second square, and t represent the time in seconds. Okay, so what about in this question? In this question, they're given the initial velocity u equal to 0. Why we know the initial velocity u equal to 0? Because the ball bearing falls vertically from rest. It is the motion is initiated from the rest, so the initial velocity is 0. Right? Then what about the displacement? The ball is move through a distance of 50 centimeter. Okay, so it is 50 centimeter. We have to convert it into SI unit, so we will get 0.5 meter, right? And they also given the time is the time taken for the motion is t is equal to 0.32 seconds, right? Then we have to find out the acceleration. Okay, which expression or which equation of a uniform accelerated motion related usta? Okay, so it is clear that the second equation relating these quantities. Okay, that is s is equal to ut plus half at square. Okay, right now we know the initial velocity. We can substitute the given values in this equation. So the displacement is equal to 0.5 meter, initial velocity is 0, and time is 0.32. Okay, so it is clear thus clear that this portion it is completely 0, goes to 0. Okay, then we have to multiply with the zero point 0.5 into 2 divided by t square, that is 0.32 all square, which is equal to acceleration. Okay, so it is we know that the zero point 0.5 into 2, what is it? It is 1. Okay, so 1, so the net acceleration, so the value of acceleration is equal to 1 divided by 0.32 square, 0.32 square. Okay, so what about the correct option? It is A is the correct option, that is 1 divided by 0.32 all square, right? Question 8: a crane lifts a container of weight 4 into 10 to the power 5 newton through a height of 25 meter. Which of the following gives the gravitational potential energy gained by the container in joules? Okay, right. Whatever the change in gravitational potential energy, change in gravitational potential energy is nothing but is the mg delta h. Okay, where delta h is the change in height. Okay, where m is the mass and mass of the container or a body, or and then the g is the acceleration due to gravity. Okay, then from here we know that what about the m into g? The product of m and g is nothing but is the weight of the container. Okay, so we can the change in gravitational potential energy is equal to weight into delta h. Okay, and we know that the weight of in this question they given the weight of the container. What about the weight? It is 4 into 10 to the power 5. Okay, then what about the change in height? Change in height is 24. Okay, it is 25 meter. Okay, so we will get the change in potential energy is equal to 4 into 10 to the power 5 into 25. Okay, so the answer of this question is second choice, choice B. Okay. Then question 9. A student measured the terminal velocity of different object as they fell through a liquid. The student used measurements and Stokes law to calculate the viscosity of the liquid. Which of the following condition does the Stokes law apply? Okay. So we have to consider the sufficient conditions for applying the Stokes law. Okay, the Stokes law only applies to small spherical objects moving slowly with the laminar flow. It does not apply to the turbulent flow. Okay, that means we have to consider small bodies, and it should whose shape should be spherical, and it should move slowly. Okay, its velocity should be very small, and the flow should be laminar. Okay, flow should laminar means there is no intermixing of fluid layers. It take place in the flow. Okay, and the Stokes law does not apply to the turbulent flow. Okay, then what about the Stokes law? The drag force over the resistive force F is equal to 6 pi eta r into V. Okay, where F is the viscous drag force and eta is the viscosity of the fluid. Okay, and r is the radius of the object. Okay, since we consider the object as a spherical body, so the only dimension required is the radius of the object, and V is the speed of the object moving. Okay, okay, so these are the conditions for the Stokes law, and the expression for the Stokes law is F is equal to 6 pi eta r into V. Okay, where eta is the viscosity, r is the dimension of the spherical ball, and V is the terminal velocity or speed of the object which is moving through the liquid. Okay, right. So the answer of this question is the body should be it should be a spherical object, and the flow should be laminar. Okay. Then question 10. The diagram shows a rocket of mass m accelerating upwards with an acceleration a. The diagram represents the forces acting on the rocket. Okay, and actually there are three forces. Okay, one is the thrust force, that is the T, and the weight of the rocket, and a drag force D. Okay, here the thrust force is acting upward direction, and the weight and the drag forces are acting vertically downward, right? Then which of the following equation gives the value of D? Okay, here we have to apply the Newton's second law. What is the statement of the Newton's second law? How we can consider the Newton's second law in this condition? If there is an acceleration in any direction, okay, if there is if there is acceleration for a body in a particular direction, then the resultant force in that direction is the inertia times is equal to the inertia times the acceleration. Okay, how we can apply this statement to different problems? Okay, let us consider ax is the acceleration of a body in x direction. Okay, we know that a body has acceleration in x direction which is equal to ax. Okay, then how we can apply this Newton's second law for that body? That is sigma fx is equal to m into ax. What about the sigma fx? That means the resultant force, the sum of the forces acting in x direction should be equal to mass into acceleration in that direction. What about the mass is nothing but it is a linear inertia. Okay, so it is clear that the resultant force in a particular direction is equal to mass into acceleration in that direction. Okay, then how we can apply this Newton's second law in our question? That means here the acceleration of the rocket is in upward direction, and what about the magnitude of acceleration? The magnitude of acceleration is a. Okay, it is given. Okay, so our acceleration of the rocket is in a vertically upward direction. Then what about the positive direction? Okay, we have to take the positive direction as the direct direction of acceleration. Okay, so how we have to find the resultant force or the sum of forces acting in the direction of acceleration? Okay, first, the force, it is thrust force, that is T. Okay, T minus mg minus d equal to m mass times the acceleration. Why the sign of mg and d are negative? Because they are acting opposite to the direction of acceleration. Okay, so this is the this in this way we are applying the Newton's second law in this question. Okay, so we can rearrange, we have to find the value of d. Okay, so we have to rearrange the terms. That means we have to put the d in right hand side of the equation, so it becomes positive. And if we are put the m in the product of ma into left hand side, it becomes negative. Okay, so we will get t is equal to t minus mg minus ma is equal to d. Okay, from here we can take the minus ma as constant, sorry, minus m as constant. Okay, so we will get t minus m into g plus a is equal to d. Okay, so we will get the right expression, or right expression of this question. Okay, so what about the exact right option? Okay, it is nothing but the d option, that is d is equal to t minus m into g plus a. Okay, where T is the thrust force and m is the mass of the rocket, where g is the acceleration due to gravity, and a is the acceleration of the rocket in upward direction, and d is the drag force. Okay, right. Okay, thank you so much.